Good morning. In my present sixth video, I would like to briefly introduce about the 2D isotropic harmonic oscillator, which is important for the CSIR gate level exams. The topic is 2D isotropic harmonic oscillator. Okay. 2D isotropic harmonic oscillator. The simple model of this system is as follows. Model of this system, that is, there are two springs and this is connected through the one mass, a single mass body, and both springs have the same spring constant, that is K1 is equal to K2. Okay, this is the model. Or we can say that omega 1 is equal to omega 2. That is omega x is equal to omega y is equal to omega. Because this is 2D model and it can be represented in XY plane. So this is the simplest model of present topic. 2D isotropic harmonic oscillator. Isotropic means same frequency. Okay. Now, what we learn in this topic, the content of this topic is that content of present topic. First, I want to know that how this simplest model is represented quantum mechanically. And in quantum mechanics, I have to know the Hamiltonian operator first. So, first we know how we can write the Hamiltonian operator in polar coordinate form. That is plane polar coordinate form, and coordinates are r and phi, where r represents the distance from the center and phi represents the angle of radial vector with x-axis. This is phi. So, and point is r phi. So, Hamiltonian is represented in plane polar coordinate. Second, after that, we construct the Schrodinger wave equation. Schrodinger wave equation is nothing. Schrodinger wave equation. The Schrodinger wave equation is energy eigenvalue equation. Energy eigenvalue equation. And this is represented as h psi is equal to e psi. So here, after this representation, h r phi gives e psi, and psi here also comes out in plane polar coordinate form. And energy of this equation, by solving this equation, we get energy which is based on two quantum number, that is n and m. So we secondly know about the Schrodinger wave equation. How can I write? And what is the output? We know about this. After that, in third content, we construct the five energy levels from the ground state to fourth excited state. And we see the degeneracy. What are the degeneracy? And the energy levels, energy of the energy levels, and how the wave function is represented by the quantum number n and m. So this is our third task. After that, lastly, we represent wave function 0, 0, wave function 0m, and wave function 2 plus minus 1 in this topic. There are infinite number of wave function, but I will discuss about this wave function. And normalization, how can I normalize this? That also deals with this topic. So first we know about the Hamiltonian of this system. For writing the Hamiltonian have two energy parts, energy operators. That is, one is kinetic energy and another is potential energy operator. Kinetic energy operator is represented by minus h direct square by 2m, because I have taken the single mass body. So this is m mass, or if I take a molecule, then we replaced this m by reduced mass mu. So here I have taken simple system, that is single mass system m, and you can replace this by mu if you take the molecules. Now, minus h direct square by 2m and del square, that is Laplacian operator, and this Laplacian operator is in R phi. This is in R phi. Another, the potential energy term. Potential energy term is also written in R phi term, and this is equal to half m omega square R square, because in Cartesian coordinate, the system is in xy plane. So the potential energy is equal to half m omega x square plus half m omega y square. But this system is isotropic. So omega x is equal to omega y, and this is omega, and the potential energy becomes half m omega square x square plus y square. But in 2D model, we know that this R phi term is represented as this figure, and here x component is R cos phi and y component is R sin phi, and by a squaring and summation of these two parts, x square and y square, the sum gives R square. So this is replaced by R square. So V is equal to 1 by 2 m omega square R square. So I have written this. Now, the task is that what is kinetic energy term in R phi term, R phi coordinates. So the kinetic energy operator is minus h direct square by 2m, and in Cartesian coordinate this is written as a del 2 by del x square plus del 2 by, okay, this is del 2 by del x square and del 2 by del y square. So by replacing these differential term in R phi term with taking x is equal to R cos phi and y is equal to R sin phi, mathematically we get minus h direct square by 2m, and this is equal to 1 by r del by del r del by del r plus 1 by r square del 2 by del phi square. One another important relation of this del 2 by del x square plus del 2 by del y square at a place of this is also written as minus h direct square by 2m del 2 by del r square plus 1 by r del by del r plus 1 by r square del 2 by del phi square. You can write any one or both. Both are equal. So here radial part of this differential radial part can be replaced by this part. And this is important for the examination. Important. Okay. Now, so we have written here T and plus V, that is equal to H. And T is ready in R phi term. So minus H direct square by 2m and del 2 by del r square plus 1 by r del by del r. This is simplest form, and plus 1 by r square del 2 by del phi square and plus 1 by 2 m omega square r square. This is our Hamiltonian. Hamiltonian is ready for the Schrodinger-Wave equation. So Hamiltonian in a R phi term for two-dimensional isotropic harmonic oscillator is written here. Okay, this is our Hamiltonian operator. Now, the Schrodinger wave equation, Schrodinger wave equation for the system is H psi, that is in R phi term, and is equal to E psi, that is in R phi term. This is the Schrödinger wave equation. And by solving this, you can consult with any textbook in which this is given. So, by solving this, we get two things here. First is energy, and second is wave function. Any Schrödinger wave equation for the system gives two things in solution. One is energy and another is wave function and the corresponding wave functions. So, the energy term and wave function term are dependent on some satisfying constant. That constants satisfy the Schrödinger wave equation. And these constants are called quantum number. These are quantum number or set of quantum. Set of quantum number. So, here energy and this function also contain the quantum numbers n and m. Because this Schrödinger wave equation is satisfied by two quantum numbers, that is n and m. So this is the output for energy and wave function also. Hence, up to this point, it is clear that energy of the system contains n and m, and also wave function contains n and m. So first of all, we see about the energy term. So the energy term of this system is n plus mod m plus 1 h direct omega. Or you can write n plus mod m plus 1 h nu. Both are equal because h direct is equal to h by 2 pi. Okay. And omega is nothing but 2 pi nu. So, by multiplying this gives ht. Now, what's the value of n? The n value is 0, 2, 4, 6, etc. All even numbers. It can take all even numbers. And m is equal to 0, plus minus 1, plus minus 2, plus minus 3, etc. So, these values satisfy the Schrödinger wave equation. So, this value comes in picture for energy eigenvalue. Now, the first 5 energy levels are written here. And for this, I have taken this diagram. The first is ground state. So, for ground state means minimum energy state. Minimum energy state. So, I have to take minimum value of n and m also. And minimum value for n and m for the energy eigenvalue, that is energy eigenvalue is this much. So n and mod m is minimum and this is equal to 0, 0. And plus 1 is in equation. So the ground state energy term is h direct omega. This is your energy, ground state term. And this is E0, 0. And wave function of this energy level is represented by psi 0, 0. Okay. So degeneracy of this energy level is 1 because only one state lies here. Now, for first excited state, since n is equal to 0, 2, 4, 6, etc. And m is equal to 0, plus minus 1, plus minus 2, etc. And for energy, expression is n plus mod m plus 1 h direct omega. So I have to take the n and m values such that this is higher than psi 0, 0, that is h direct omega, that energy value h direct omega, not too much higher. So in this regard, I have to take n is equal to 0 and m is equal to plus minus 1. Because if I take n is equal to 2 and m is equal to 0, then the summation gives 2. That is higher than 1. So I have to take summation value 1 first. So here there are two combinations. First is 0 plus 1 plus 1 h direct omega, that also gives 2 h direct omega, and 0 plus mod minus 1 plus 1 h direct omega, and this is also 2 h direct omega. Hence, the second excited state. The first is our h direct omega, and this is 0, 0, and psi is 0, 0. Second energy level consists two states, but both having energy 2 h direct omega. But states are not same. States have different quantum numbers. One having the 0 and plus 1, and another having 0 and minus 1. So there are two degenerate states there. So the degeneracy goes to 2. Here degeneracy is 1, only 1. Now, for second excited state. Now, for second excited state. Second excited state. Again, n is equal to 0, 2, 4, 6, and m is equal to 0, plus minus 1, plus minus 2, plus minus 3. So I have to take greater than 2h direct omega energy, not too much higher. So energy is equal to n plus mod m plus 1 h direct omega, and n plus m mod m, that greater than 2, just greater than 1, just greater than 1 is 2. So I have to take the pair 0 and plus minus 2, that also gives 2, and also 2 and 0. This also gives 2. So there are two combinations here, n and mod m, that gives 2. If I take n is equal to 0, then m is plus minus 2. That also gives 2. And if I take n is equal to 2, then m must be 0. So gives 2. So here there are three combinations. First is your psi 0 plus 2. Another is 0 minus 2. And next is psi 2, 0. All are different because their quantum numbers are different. So the configurational coordinates are different. Configurational coordinates gives different representation. Different representation in polar plane. Okay. So if quantum number of state functions are different, there are different sets, then configurational coordinate gives different representation in space. Hence, these are different. But energies are same. Energy for these three states are 2 plus 1 h direct omega, that is 3 h direct omega. So these three states have same energy, each having energy 3 h direct omega. Hence, the second energy level, we see that in ground state, the energy is h direct omega. In first excited state, there are two states and the energy is 2h direct omega. And second excited state having energy 3h direct omega with degeneracy 3. And these are 0, 2, 0, minus 2, and 2, 0. Similarly, take another example, that is, this is second excited state. Take third excited state. Third excited state. So this is third excited state. So I have to take here n plus mod m is equal to 3 for third excited state. Because for 0th excited state, we have taken n plus mod m is equal to 0. And for first excited state, we have taken n plus mod m is equal to 1. So, and for second excited state, I have taken n plus mod m is equal to 2. For third excited state, I have taken the here n plus mod m is equal to 3. And this combination gives 4 states. See here, n is equal to 0, 2, 4, 6, etc. And m is equal to 0, plus minus 1, plus minus 2, plus minus 3, etc. So, the combination have the value 3. The first pair is 3 and 0. That is 0 plus minus 3. This is first pair. Second, because n is 0 and we cannot take n is equal to 1. We can take n is equal to 2. So, if n is equal to 2, then m is equal to plus minus 1. Such that so that a mod m gives 1. Hence, there are 4 degenerate states possible. That is psi 0 plus 3, psi 0 minus 3, psi 2 plus 1, and psi 2 minus 1. And all have the same energy eigenvalue, that is n plus mod m plus 1 h direct omega, and this is equal to 3 plus 1 h direct omega. This is 4 h direct omega. This is your third excited state. Hence, up to this point, we have taken 4 levels and their degeneracy are following. That is for ground state, the degeneracy is 1. For first excited state, degeneracy is 2. For third excited state, degeneracy is 3. And for fourth excited state, degeneracy is, take this here, fourth excited state, degeneracy is 4. Okay. And energy eigenvalues are h direct omega, 2h direct omega, energy is 3h direct omega, and energy is 4h direct omega. This is your ground state. This is your ground state. This is your first excited state. This is third excited state. Yes, second excited state. Second excited state. And this is third excited state, having degeneracy 4. So, for fourth excited state, we can say here that G must be 5. And we can see that for E is equal to 5h direct omega, or for fourth excited state, n plus mod m, that must be 4. And n is equal to 0, 2, 4, 6. M is equal to 0, plus minus 1, plus minus 2, plus minus 3, plus minus 4. Hence, by making the pairs, by pairing n and mod m, we get, if we take n is equal to 0, then mod m must be 4. So, m is equal to plus minus 4. This is first combination, if n is equal to 0. Next, n can take value 2. So, n is equal to 2, then m must be plus minus 2, so that mod m becomes 2 and n plus mod m becomes 4. Now, the third pair is n may be 4. So, n is equal to 4, then m is equal to only 0. So, here there are 5 degenerate states, and these are symbolized as psi 0 plus 4, psi 0 minus 4, psi 2 plus 2, psi 2 minus 2, and psi 4, 0. So, we have seen here that the degeneracy of each level increased by 1, and energy also increased by 1 with the constant h direct omega. And states have the different combination of quantum numbers. So, you cannot assign smoothly that this function is for this energy level. You have to take pair and then you can assign the wave function. So these are the brief introduction about the energy levels. Now, I have to write the wave function in R5 form, because we have seen that what are the energy levels and how many states are in energy level. So some energy states you can write, not all, but some energy levels you can write that are important for examination. So for examination point of view, I have introduced 0 and m. 0 and m combination wave function. And that is simple to write. And this is equal to 0 and m. This is equal to psi 0, 0 or psi 0 plus 1 or psi 0 minus 1, or you want to write psi 0 plus 2, or you want to write psi 0, any combination having the first digit is 0. That is n value is 0 and m is anything. So for this wave function, the shortcut is that 0m is equal to n times, n is the normalization factor, and r to the power mod m, or e to the power minus alpha r square by 2. And for m, that is e to the power mi5 here. So this function is given for the 0 and m combination here. And normalization factor is calculated by, this is calculated by equating the probability total probability is equal to 1. So I have taken the simple example, that is simplest example 0, 0. So for 0, 0 state, you can write r to the power 0 and e to the power minus alpha r square by 2 and e to the power 0, that is m is 0, so this is 1. So the psi 0, 0 have simple form e to the power minus alpha r square by 2, but having a normalization factor. What is this normalization factor? So for this normalization, the equation is psi star psi d tau, and this gives 1. What is the value of d tau? This is the another important term for the 2D harmonic oscillator. So now we will see what is the value of d tau. Then we calculate the normalization constant. So first of all, I have to see what is the volume element for the two-dimensional harmonic oscillator. Okay, for two-dimensional harmonic oscillator. And this is important term, another important term for the examination. in plane polar coordinate. That is in R phi. So now we are going to represent d tau in R phi term. Because in xy plane, this is simple. D tau in Cartesian coordinate, this is simple, dx into dy. Nothing else. Dx into dy. But I have to represent this in R phi term. So what is the value? So for this, you take a plane, xy plane, here, and take a point P, radial vector is R, and this P point is written as R phi. This is the polar coordinates. You call this plane polar coordinates. Now, since x component is equal to R cos phi and y component is R sin phi, but I have to represent d tau. So for d tau, that is dx into dy. This is nothing, but this is dx and this is dy. Then this is the increased change in area. So I have to construct a change in area by increasing r and increasing phi. So for this, I have taken this picture here, and this picture is that this is P point. So I extended this radius to dr. And now we move this radius through d phi angle. Okay, this is d phi angle. Now, what is the increased area here? Change in area. So first of all, if the radius is r, then changing is nothing. This is the area that is constructed by d phi. But by both dr and d phi, the area changed by this figure, and hence this figure becomes, this is dr and this arc is equal to r d phi, and now this changing area is equal to r dr d phi, and this is nothing but this is the dx and dy. So dx into dy, that is d tau, is equal to r dr d phi. This is important for the examination. In two-dimensional plane polar coordinates, the d tau is r dr d phi. And the range of r is 0 to infinite and range of phi is 0 to 2 pi for constructing the plane, that is circular plane. Okay. Now, so I have to find normalization constant. Normalization constant for the n value 0 and m value 0 state. That is psi 0, 0 state. And we have written that psi 0, 0 is nothing but r to the power mod n and e to the power minus alpha r square by 2 and e to the power 0 I phi. And this is the normalization. So for this function, this is 0, and so r is r to the power 0, that is equal to 1. So e to the power minus r alpha r square alpha by 2. This is the psi 0, 0. Now, for normalization, the equation, probability equation for this function is n square e to the power minus r square alpha by 2, and squaring this and r dr, and another term is d phi. But phi terms is not here. It means not 0, but this is 1. So d phi, I have to take the d phi, another term, in for d term. So this is 0 to 2 pi, and this is 0 to infinite, and this total normalization, total probability is must be 1 for this function. Now, what is alpha? Alpha is nothing but this is the combination of the constant. So this is equal to m omega h direct. This is the combination of constant. A mass of the system is constant, frequency, angular frequency is constant, h direct is constant because this is quantum mechanical system. So mass is in the range of, mass is in the order of h. And this is also equal to root under k and m by h direct. This can also written at this much. So here alpha is nothing but this is constant, and r is the radial vector that goes from 0 to infinity, and pi goes from 0 to 2 pi. Now, this is equal to 0 to infinity, and this is equal to e to the power minus r square alpha, and this is r dr, and d phi 0 to 2 pi is equal to 1. What is the solution of this equation? So n square into the integration of this part is gamma 2 by 2 by 2 into, here constant is alpha, so alpha to the power gamma function, the gamma function is 1, and now this is equal to 2 pi, and this is equal to 1. Here, this is equal to gamma 1, and gamma 1 is nothing but factorial 0, and factorial 0 is 1. So by solving this, we get n square into pi by alpha is equal to 1, and this gives n is equal to root under alpha by pi. Hence, the normalized ground state function, is equal to 0, 0. This is equal to root under alpha by pi, and r to the power 0, that is 1. So e to the power minus alpha r square by 2, and alpha is nothing but m omega h direct if the potential is your half m omega square r square. So this is the final output of the system, and energy of this 0, 0 function is h direct omega. For my 7th video, we will discuss about the degenerate perturbation theory by taking examples of two-dimensional isotropic harmonic oscillator. So in this video, we will see how can write the psi 20, psi 2 plus minus 1, psi 0 plus minus 1 etc. We can write in this video. We can deal the degenerate perturbation theory on the basis of this function. So I last this video here. Thank you. है ना?